factors which may be an important factor, for the serviceability of the structure, we may miss out. So that is the point. Similarly, why I am giving this example, the very basic reason is that when we are doing the seismic design of any structure, whatever hypothesis available to us, based on that, code was modified and we are using those particular codes. So that's why my point of saying is that every earthquake gives a new lesson, which subsequently being analyzed by the research community, and sometimes some particular hypotheses are being developed. So that's why there is no end about the concepts in seismic design of foundation, or you may consider as a structure. Now, directly going to the some of the case studies of seismic events, where we can see the structural failures. We can see, especially the bridge failures. You can see in different earthquake events. For instance, 1964 Niigata earthquake, where the bridge of Showa Bridge in Japan has collapsed just like anything. The central piers were collapsed, right? Then similarly, in the year of 1964, also another earthquake, Million Dollar Bridge also collapsed during Alaska earthquake. Then you can see some earthquakes are being referred as 1995 Kobe. And most importantly, in our country, 2001 Bhuj earthquake also given some evidences of failure of some port structures which were supported by well-engineered pile foundation. So this gives a lesson. This why I am mentioning these particular earthquakes today. I will show you most of the cases are case studies, which primarily gives an idea about the lessons learned from the failures of these structures. And today we are in a such a position. We are in a such a position that this particular following these particular evidences of earthquakes, today our internationally our code has modified a lot. So till now also, in future earthquakes, for mitigating the future earthquake events, one designer should be aware of some of the hypotheses which should not be missed out, considering the importance of the structure lying in the seismic zones. With this, let me just discuss about some of the physics of the problem. This is, all of you know that a building or bridge structure, heavy structure supported on pile foundation. It may be an ordinary pile foundation, it may be pile ground foundation, whatever may be the thing. Am I audible? Hello? Hello, am I audible?
Yes, sir. Yes, sir. You are very much audible.
Yes,
Okay,
sir. You are audible, sir. Please, sir.
Okay.
Yes,
Okay.
sir. Yes, sir.
Okay, thank you. Thank you. So you see, this particular structure, all of you know this particular type of structure which is supported by well-engineered pile foundation. So today's talk, I will be mostly focusing on pile foundation. The reason is that all of you know that the structure which are being withstand or being supported by pile foundation is a very robust and well-engineered foundation. Even if in soft soil, alluvial soil, these particular type of foundations are oftenly used for supporting the structures. So what are the common in these structures? Pile foundation slender members are there, then supported by raft or sometimes pile cap and the building. So a complex mechanics going to happen, a complex interaction, rather mechanics, I would say interaction. Okay, the interaction going to happen over here during this seismic event, right? This is a complete dynamic interaction is going to happen over here. If you missed out this interaction, it is observed that the reason of the failures is because of the missing of the interactions, right? This is one of the issue. So let us try to highlight this interaction part, that current understanding of file failure, that what the international code says about the failure of the present condition, present understanding. You see, if there is a deposit of liquefiable layer, hopefully you can see this is the failure of the, hopefully, the Kanla port, or in case of Japan, I think this failure was observed, where you can see that non-liquefied stabilized crust is there, and there is followed by a liquefied layer. In such cases, Why the reason of failure has happened? Because because some of the issue may not be addressed earlier, and followed by this earthquake, this particular design provision has come up. You can see Japan has first introduced this concept. If you see the bottom figure, where if there is a presence of liquefied layer, na, that depth is being represented by HL. If there is a liquefied layer, then we should consider some thumb rule has they have given 30% of the total passive resistance we can consider as a passive, because the passive resistance gets subdued when there is a liquefiable layer or liquefaction happens at certain conditions. And what happens? This liquefiable layer gives additional stress on the pile, and obviously the pile are not being designed for that additional stress generally conventionally, and that may lead to the failure of such events of which you can see in the past. Just following this particular slide, later if I go to the in-depth into the matter, you see the Japanese code in 1996, they've given this idea, they identified the problem of the liquefied layer where the foundations are being designed considering 30% of the total overburden pressure as the lateral resistance. But ultimately it is found that this lateral resistance, this lateral resistance is questionable. This lateral resistance was questionable, which was published in 1996. So 30% of the total overburden pressure, right? So presently people are being arguing that, oh, okay, that this pressure should not be there and there will be no passive resistance, something like that. So there is way, so if there is a passive resistance, generally a bending mechanism going to happen. If you just forget about the passive resistance, then obviously the bending resistance will not come into picture. I don't know why it is coming. Just a minute. Okay, fine. So these are the issues they saw. What they saw, the structural engineers washed their hands and passed the problem to the geotechnical engineers. The geotechnical engineers saw that the building moved towards the quay wall and in some cases towards the slope. They thought that it obviously that the soil lateral spreading caused the piles to collapse. So what happened in such cases of failure? Structural engineers just generally gives an understanding that there will be no failure in the structure because of the foundation failure. The structure has been deformed, or there will be a tilting of the foundation structure. Might be the reason is the for the geotechnical engineer they have not considered the design. But you know actually what happens, some of the mechanics that that after this failure people have identified, after this Japan earthquake failure, people have identified one term, lateral spreading. Lateral spreading is one of the event where if there is the presence of liquefied layer, or over the top if there is a non-liquefied layer which is being lying in a slope, that give a huge moment on the pile, right? Bending moment, which may cause a bending moment. That is called kinematic interaction kind of thing, right? So failure in level ground and sloping ground. Level ground also we have seen several failures. In sloping ground, you can see this is the example of the 2001 Bhuj earthquake, which evidenced this kind of failures. And this failure is caused because of the subsidence of the pile, sudden subsidence of the pile at the bearing level. Now you can see bridges in liquefiable areas, often only bridge pier fail, not abutments. You see, if you categorically observe these failures, Alaska bridge failure, during Alaska earthquake, and the failure of this Niigata earthquake Showa bridge, the observation is that the abutments has not been failed. Interestingly, the central piers has been failed. So obviously, people are behind behind that. What is the reason? You can see this figure is an old figure. The Niigata earthquake, the central piers has been failed, not the abutment level. What is the reason? So people have tried to investigate the reason, and different school of thoughts are available today with us. Now check the factor of safety against GRA. The GRA means Japan Road Association has given some basis of analysis how you will find out the moment capacity of the pile based on these assumptions. They have checked. So while checking, they found that conventional code cannot define the failure. Rather, some of the additional analysis has understood that no, there will be some gaps are there which cannot alone cannot define the failure mechanism. So finally, it has been come out that some missing links are there. You can see a good photograph over there, 1964 negative earthquake. This failure, you can see over here, the central pier has been collapsed, right? There will be material failure of the piers, I mean the piles, steel piles. Okay. Now, based on these failures, Bhattacharya has done a lot of research in this direction. They have tried to give several ideas about the failure of the pile foundation, from which some design guideline has been framed out. The first figure is showing if the particular subsoil layer is a loose sand deposit over which some non-liquefied crust layer is there, only static loading you are considering, then obviously pile will generate the skin frictional resistance and the unbearing resistance based on which the pile will be, the total structure will be lying. On the other hand, if you considering the dynamic loading during the seismic excitation, if you see if the piles are if the liquefaction gets started, then what will happen? Stage 2, shaking starts, soil yet to liquefy, pile acts as a beam. These piles are acting as a beam member, right? And just in the stage 3, where we can consider soil has been completely liquefied, right? Inertia forces may act, pile acts as a column. Then you can consider the piles are acting as a column. So now the question is there, when you will consider the pile to be acting as a beam, and this transformation from beam to column, understand column mechanism, column behavior of the pile, it depends when the sand has been completely liquefied. So there is a transformation of understanding, right? After these theories has come up. So today's design, you have to consider this particular for particular research, and you can design. When you are considering the design of a column, the pile will be acting as a column, then bending, buckling, both the mechanisms are coming. And when you are considering only beam theory, only bending will be considered. Bending moment will be considered for finding out the maximum moment capacity. Whereas when you are considering the piles are acting as a column, then obviously you have to consider the column. Obviously, columns are going to fail depending on these two criteria, bending criteria, as well as the buckling is also another important criteria. So what actually Bhattacharya wants to give. So afterwards, he has shown the back case studies. Several case studies are being represented over here. Hello, am I audible?
Yes, sir.
Okay, so several back analysis of 15 case study failures were taken, and they have identified that what will be the diameter of the pile, or some effective lab consideration was considered, and radius of gyration was considered, and they tried to segregate these two areas. One is poor performance of pile during the earthquakes, and good performance is there. So from that, they have tried to identify what is the effective length of the pile, and based on this such criteria, they are safe against buckling, and beyond this zone, red line zone, it is so these are several theories they have given. Now, based on this theory, actually the yield stress versus L effective length, this some graphs were prepared to identify the good performance and the poor performance. And Euler's theory, all of you know that Euler's theoretical curve for M25 concrete, while this red line is showing this Euler's theoretical line to basically make you understand about the buckling theory, right? Next is practical implications. Apart from writing a new design method to incorporate buckling, we have to evaluate the safety of the existing pile foundation in seismic areas. Now, criticism of buckling instability theory was also made in several research. What exactly it states about the buckling instability, that why the piles are failing. We are defining the piles are being failure by buckling. A group of people are not going to understand this particular mechanism. Buckling is not possible for such a solid pile. They are trying that no, there will be some flexural kind of failure is going to happen. So there is a criticism of buckling instability theory, and they tried to make it a kind of shear failure or flexural failure kind of thing. So there is a debate, right? Now, if you go back to if you see the vibrational characteristics of pile foundation in, liquefied soil, you will find a significant zone, which natural frequency, if you see, that varies from 20 to 140 hertz, right? Omega 1 is 20% to 140% is the extent of I mean increase in time period of it was made of a P by P critical, right? Therefore, we need to find out the dynamic bending moment of the pile as the soil liquefies. That is, by dynamic bending moment is important. So these are case studies again, similar way they have tried to understand. No, now that you see the idealization, they're a very important thing. If you consider a structure by this Lampas model over a pile foundation, if there is no liquefaction, you can consider the first model. But if there is a liquefied layer, obviously during the liquefaction, we have seen this this particular depth of pile foundation loses its lateral resistance. Then this problem of the whole structure is considered as a soft story idealization. This particular zone is considered as a soft story. You see, the effective length of this pile are going to be increasing, and you consider the depth of fixity over something like that as a non-liquefied layer. So there is a very purely change in idealizations. If you are not non-liquefiable soil, you can consider a simple idealization of this, where the depth of the foundation is very less. So already I have mentioned these theories that is being analyzed of the pile supported bridges. Post analysis were made by these idealizations, and people have tried to identify what is the mechanism behind the failure, and they ultimately find that some linking, some actually some good understanding about the complex interaction mechanism was missed out during this design of these bridges, which basically mainly the reason of this failure of this bridges during this earthquake event. Afterwards, the codes were modified, keeping view on the lessons from these particular earthquakes. I mean, bending, buckling mechanism, lateral spreading mechanism, which was not earlier in the code, right? Now, depending on this future work was planned out. Okay, so whatever just now, obviously pipelines in seismic areas. Okay, so you see, this is very important when you are considering any seismic area. Suppose a pipeline you are going to design, and the pipeline has to pass through a seismic region. So, what are the precautions you have to take care of? And these particular precautions you have to take care of while you're designing. So that's why when you're designing any structure in seismic areas, you should look into several aspects. I'll show you other aspects also, just quick. So how much time is left for me?
Sir, you can continue. We can continue up to 5 to 10 minutes if it is possible, sir. Or if you need more time, we don't have any problem. We can continue this.
Okay, I can continue 1 hour, but there should be a reasonable limit. I understand. The internet connection gets unstable. Let me finish up, huh? Because
sir.
mobile is not.
Yes, sir. Yes, sir. Yes, sir. So it was about to be completed within 7:30. Although there is a technical glitch, that's why the time has been a little bit extended. So up to 10 to 15 minutes, is it okay, sir?
Let me try. Yeah.
Okay. Okay, sir. Sure, sir.
So just giving a touch about the basics of earthquakes from this point of view. Just now, whatever preceding, I have shown you some of the case studies and what are the advancements in design concept were made. Just I think audience will be very happy to hear the basics of earthquakes. I'm not giving much time on the basics, but just I'm telling you some of the things which in the previous very ancient time, what exactly people understands about an earthquake. The myths, mythology, right, behind this earthquake. This is a very important slide. I found out that people in the ancient time understood that the earth is held up by four elephants that stand on the back of a turtle. The turtle is balanced in a turn of a cobra, right? In a turn of a cobra. Why? When any of these animals moves, the earth will tremble and shake. That was the concept in the ancient times. This was the concept. But truly, the mechanics science is something different. I hope you all understood these mechanics, right? So an earthquake is a sudden rapid shaking of the earth caused by the release of strain energy stored in the rocks, right? All of you know the basics of the origination of earthquake energy. So I'm not going into much about this. Let me go to some of the mechanics. So I'm just skipping these slides, layers of earth and how the earthquake occurs, the convection energy comes up. So these things I just skip. I know all of you know these parts. And this is more important, that seismic zones, rings of fire, which part is called as rings of fire throughout our world, where the maximum earthquake activity happens. These rings of fire is an important, I mean, in line in so that you can have a decision of the designing of some structures in these seismic areas. So I'm this skipping all these basic things. I hope you are. Now this is a very close picture about the San Andreas Fault, which people who knows it was in lying in California, near California, and people used to go. It is a tourist spot also. People used to go to see this active fault, which is visible by open eye. Right, San Andreas Fault. It's a very lively active fault, which you can visibly you can see something like that. You can see over here. So just this, and so I'm just skipping this part. Now I'm coming to the seismic hazards. If you quantify the seismic hazards, what are the seismic hazards? Probable seismic hazard people have understood. That first is seismic shaking. The shaking, how the shaking varies from place to place, then liquefaction, then permanent ground deformation that is caused by lateral spreading or landslide or faulting. And finally, we have also experienced the event of tsunami during an earthquake. So all these hazards we should know, and how to cater these hazards, or how to balance or to mitigate these hazards from the point of view of designing the structure, that we should know. So major seismic hazard that affects structural performance will be discussing seismic shaking. Now let me go to the seismic shaking part. If you see that I'm just trying to show you some of the ground motions, some of the ground motions. You see there is a variation in the signals. The point you have located, there is a variation in the signals. What is the reason? The seismic shaking also, if you closely observe, there will be wide variation in the signals, right? The reason is basically when passing through the wave, when the when the waves are passing, so when the waves are passing through this different soil medium, then it gets attenuated. And this occurrence of seismic forces will be different from a place to place for a single earthquake. That is the understanding of this figure, that is the seismic shaking. Quickly, I'm just passing through this. This is a repetition of this slide. How to find out the location and magnitude of an earthquake. There is a basis is there. I'm not going to discuss. How can you, from a signal, from P wave and S wave, the geophysicists are going to calculate what will be the epicenter of the earthquake and what will be the probable magnitude of the earthquake after studying the whole signal. First part is the P wave, then obviously the second shear wave is going to come. Next, just quickly, I have to finish. I understand your condition. Yeah, that is a very important photograph. We could find out that 1897, all of you know, there is a mega earthquake, more than 8 magnitude in Assam earthquake. And what people have observed, up throw of boulders greater than 1 G. That means boulders have been upthrown because of this vibration. Can you imagine? Just near the epicenter, right? So this was the tremble, you can see, you can understand. Now ground shaking effects on structures. If you see, there is a Greek symbol of plus symbol. What is the understanding? That the left hand side, when you see the ground shaking effect on the structures, you will find ground shaking causes the structure to vibrate it because of inertial involvement. All of you know that dynamic forces involves one of the major forces, the inertia force. And right hand side, if you see the another category of failure of the structure, it is found out that they have quantified there is a kinematic effect. There is a two effects are there when the ground shakes on the structure. One is inertial effect, another is the kinematic effect. So if I get time, I'll obviously try to discuss. I'll be happy to discuss. Now, what is ground shaking effect? Now, ground shaking effect that clearly indicates a picture of Mexico City earthquake was shown over here. A case study of a Mexico City earthquake was shown over here, where we can see a complete damage of a particular structure of height of, I think, 6 to 15 stories building on height are got severely damaged. What people have observed? There was no liquefaction cases. No faulting was presenting over there, active fault. No landslide. Some settlement could have observed. What is the reason of such failures? So ground shaking effect has caused this particular failure. That means the motion at those particular zone has some characteristics which tuned up with the tuned up or resonating condition has been developed or with the natural period of the structure, and the ground period has got, I think, messed up. So that was identified as a reason. So ground shaking effect is an important issue when you're designing the structures. Then obviously you can see the Mexico City earthquake in a close view. You can see soft lake bed deposit under Mexico City causes large amplification of ground motion. This is called as this particular area is called as a local site effect. You can see the Mexico City. This is the profile. Bottom end you can see the profile. There is one side is hill zone and another side is the bed of volcanic ash soft clay layer. And what happened when there is Mexico is a place of earthquake, and what happened, because the waves cannot dissipate it out because of the hill part. Boundary condition was very rigid, so that's why the energy gets entrapped into the soil bed, I mean soft soil deposit, lake deposit, and because of this higher energy it was heated the structure. Those particular structures, 6 to 10 to 12-story building, has been damaged. It was mentioned 2 second period structures has got resonating effect. At least what happened, the ground motion has got sufficiently attenuated and significantly attenuated that 2 second period of structures got resonated or be tuned up with the motion at the bed level. So this is very quite interesting. These are the examples, right? Now you see ground shaking effects on structures. A complete structure pile supported structure has been uprooted. It was found that the piles are being designed to particular support the structure was friction piles. Okay. And because of this effect, ground shaking effect, it was uprooted. You now understood what kind of failure can be anticipated from such earthquakes. Now, just ground shaking effect on structures. There are a number of cases out there. I think this is the case of another buildings where in Bruges earthquake also, several earthquakes we have seen ground shaking effect has caused particular structure to fail. For particular period of structure has been failed, right? So I think I should stop over here up to ground shaking effect. Obviously, if, ground shaking effect on structures, you see, people have asked, what is the mode of failure? Such failures of a long expressway is called Hansin Expressway in Japan. What is the reason? Because of ground shaking. That means there might be some variation in the ground shaking which is caused by the particular earthquake. So it was identified that soil structure interaction was missed out. This particular analysis and found they've reported that 25% higher response was there when you consider the soil structure interaction. So that means soil structure interaction is another important missing link in the design earlier than this earthquake, 1995 earthquake, which was finally further quantified in the design codes and addressed accordingly. So up to this much, I think I can address over here, as I have a lot of things up there, I believe, but I have to stand somewhere. I have to stop somewhere. So this ground shaking and the soil structure interactions, and these are the case studies I have discussed today for giving you a better understanding of the design of the structures. So with this, I just stop my presentations over here, understanding the fact that power power problem as well as some issues of these internet issues are there. So that's why I want to be more meaningful over here. Over to organizers. Thank you.
Thank you, sir. It was a wonderful presentation, and I hope that all the participants of this FDP have gathered a lot of knowledge from your presentation. We, on the behalf of the organizing committee, are too much thankful to you for responding to us for a very short time, and hopefully, near future also, we will get your help whenever it will require. So, thank you, sir. Thank you again very much. And now it is a question answer session for the participant. If anyone is interested to ask anything or clear some doubts regarding to this presentation, sir will be answering all the questions of the participants. Now over to the participants. If anyone have any kind of doubts or anything to share. Any questions from the participant side? So I think there is no doubt or any confusion regarding this topic that you have discussed, sir. So again, we are very much thankful to you for giving your valuable time, and thank you again.
Thank you, everyone, for joining with and giving patient hearing me. Obviously, end of the day, it is very tough. I understand. Obviously,
Yes.
question may be there because instantly it may not come to our mind. Obviously, we
Yes.
also sometimes think of. So, if anybody is interested, please visit the website. Collect my contact number. It is available in the website. Anybody interested, they may email me or we can personally talk also. We are always welcome participants from my side. So thank you for hearing me again and giving me the opportunity to speak in this platform of tech organized by Techno India Group of Engineering Colleges. I wish all the best for this particular FDP program for the next 5 days. Thank you, Rahul, Professor Rahul.
Thank you very much, sir. So it was from the side of Dr. Saha, who has joined us for this presentation over the foundation design in seismic areas. We are thankful to the participant for patiently hearing to us, and we'll be joining for the next session tomorrow at around 6:30 p.m. So I will request all the participants to join within 5 to 10 minutes prior to that. That is around 6:20 to 6:15. And tomorrow, Mr. Bikram Shaha will join to us. He is an assistant professor in the field of civil engineering from TTADC Polytechnic. And he will be sharing his views over the groundwater wells, reservoirs, and all other liquid retaining structures. So with this note, I am here ending this session. I hope that it was a valuable session for all the participants. Thank you. Good night.
Thank you, sir.